So hello and welcome to this A2EP webinar on 3 ways to avoid a costly electrical upgrade. Today we've got a fabulous set of speakers here for you, and we're going to go through these 3 main steps to avoid that costly upgrade. Of course, that's going to be getting the right data and controls, energy efficiency opportunities, and then looking at solar, PV, and batteries. And we'll end up with a Q&A, so hang around for that one and be ready with your questions. My name is Jared Leake, and I'm the CEO of the Australian Alliance for Energy Productivity. As always, I'd like to start this webinar with an acknowledgement of country and acknowledge the traditional custodians of country throughout Australia and their connections to land, sea, and community, and pay our respects to their elders. This webinar is brought to you by our wonderful set of members. These members share our vision to improve energy productivity and decarbonisation across industry and commercial sectors in Australia. And without this wonderful broad cross-section of members, we wouldn't be able to bring you this webinar here today. So thank you to our members. I'm flying solo today, but here is our team. I do have a great panel here to help me out with the Q&A and what have you, but just you got myself here today. A little bit of housekeeping. We will record this presentation. We will have the slides and Q&A answers sent out to you usually within the week or so. If you do have questions, please pop them in that Q&A box, or feel free to have a sidebar discussion in the chat window. We'll have our presenters and panel there to answer your questions as they go and as they finish their presentations as well. So lots of interaction there for you. Just a little bit of scene setting before we hand this over to our first speaker. This webinar is coming on the back of the webinar we did last month on electric options for storing and supplying decarbonised industrial heat, where we talked a lot about these etes solutions. And that leads to a lot of questions about poles and wires and upgrading, hence the webinar today. From that webinar, we saw that the main vector for decarbonisation, the technology, is electrification. And so that's where we have that focus. And this came from that boiler study that we did last year. We had some great insights coming from Rondo showing how most of the time, more than 50% of the time, the price of electricity is less than the price of gas plus carbon. And so making such electrification solutions definitely viable. We also saw from Essential Energy, and we'll see a little bit more today about this new solar soaking tariffs that are going to come out, and it's going to be an excellent enabler for electrification. And just give this a little bit of context what we're talking about here today. So we know it's so common for most industrial sites that for them to electrify, they need a much larger connection. However, we're sure that a hybrid solution is going to be the way forward, and we're sure that there's things that can be done while you may be waiting for that larger electrical connection. And that's what we're here to address and explore today. And so if that orange line there is your load, electrical load during the day, and you have the peaks and troughs and what have you, then we'll present today. So let's look at how can we reduce some of those major peaks, and how can we reduce the average load as well through energy efficiency, and finally, how can we increase that sort of available electrical load there with some solar and PV, solar PV and batteries. So to explore that today, I've got these. We've got put together these fabulous speakers. We have Ian Askell from Essential Energy, James Diliberto from AZZO, Craig Morgan from Northmore Gordon, and Stace Tzamtzidis from GridBeyond. And so we're going to kick off with a little bit more scene setting. I've got Ian Askell here from Essential Energy, and Ian, I'll ask you to come off mute and start sharing your slides. Ian is an electrical engineer with over 20 years experience in the industry, and he's heading up the program within Essential Energy, looking for electrification and key accounts. Essential, as far as we can see, they are absolutely leading the way when it comes to distributors working with customers of how to electrify and decarbonize. So we're very, very pleased to have Essential presenting on how this can be done and the different programs they're working with this. Ian, over to you. We're in your hands.
Thank you, Jared. Can everyone see the slides?
Yep, I've got them here.
Fantastic. All right. So just recapping, some of you may have attended the previous webinar that Jared mentioned, but in terms of our network footprint, so we service about 95% landmass New South Wales, regional rural New South Wales, and we've got connected about 900,000 customers across our network. Some key messaging here that I talked about last time is about 1/3 of our network operates at zero carbon in the middle of the day. This is driven by the significant uptake of renewables on our network, where we've got connected about 2.2 gigawatts rooftop solar PV, so that's mums and dads and small businesses with solar panels on rooftops, and about another 1.5 gigawatts large scale. And this is growing every day, and it's great to see in terms of the rapid reduction in the carbon intensity of energy delivered through the grid. Just recapping our electrification program. So I head up our electrification team at Essential Energy, and it's very much focused on supporting customers on a least cost path to decarbonise. And we're seeing by driving network utilisation, as I discussed last time in the last presentation, in terms of we operate under a revenue cap. So if we can manage peak demand, that is the asset base remains fixed, and we can increase network utilisation, the unit cost of the network should reduce in terms of the dollar per kilowatt hour delivered. So that's very much what we're looking at as part of the program. And I think the focus today is there'll be some other presenters talking about behind the meter solutions, but we're also looking at some demand side solutions with customers I'll talk about and trialling. Before I get into that, I'll quickly just have one slide on how we plan and design the network. So in terms of underlying load growth, or when new load connects to the network, we typically assess two scenarios. So that's peak load in terms of maximum load on the network and minimum load. And on the right-hand side, there's one of the examples we assess. So we assess thermal limits, voltage limits. We must maintain voltage within set limits in terms of supply to customers. And there's also fault level analysis that's completed as well to ensure adequate protection coverage. So I've just taken one of these examples around voltage assessments, where traditionally we would focus the network on supplying peak load, so we'd be concerned with voltage drop. But now with the uptake of renewables, we're now looking at voltage rise during minimum demand. And this is what we call widening of the voltage envelope. And I'll talk a bit later when I talk about network tariffs and some innovative solutions we're looking on the demand side as a lower cost to try and manage that and connect additional renewables and load to the network to work within the physical limits of the network without expanding the network. So typically when a network constraint arises, we can either change things on the supply side, which I'll talk about on the next slide, or we can look on the demand side. So we're physically shifting demand around, so demand management techniques. So on the supply side, when we hit a network constraint, we typically look at a couple of options here in terms of basically reducing the supply path impedance so we can increase current and reduce voltage drop. So examples of that include reconductoring, so basically bigger size conductor. We could include additional circuits or feeders. We could increase the voltage, so say doubling the voltage, double the power through the same line, or increasing larger transformers. A couple of things to note here is that augmentation of the network, so when you're physically reconductoring or increasing a transformer, there's typically step changes in capacity. So that's something to note in terms of when capacity is added to the network. When I've got a couple of notes here to think about that when you're adding additional load, it's best to think about your future requirements, noting that the granular steps in terms of capacity, how it's added to the network as a supply side. I've also just noted the Pioneer scheme here, which has a link. So to explain how that operates is when a customer connects additional load to the network, if they trigger network augmentation, or there may be a HV extension. This scheme typically lasts for 7 years. So if additional customers connect into that network that was funded by the original customer, they're then reimbursed for the second customer that's connecting to that asset. So I do encourage reading that guide, which is on our website, and how that scheme operates. And this is more about trying to share that cost in terms of using the network and trying to minimise connection costs. And then thirdly, another point I'd like to raise, which is part of our electrification program while we're mapping fossil fuels, is from a systems level planning perspective. If we had visibility, say with an industrial state or total across the network, the potential electrified energy in demand, we can plan the network from a system level. So this supports our strategic planning process in terms of minimising the connection costs, looking at the granularity of network augmentation, noting if we've got that data at hand, which there can be challenges where we're saying where a customer may submit a connection application, that if there's augmentation triggered, if there's a single customer, but if there's a group of customers, you think about that connection cost is reduced because it's shared across a greater number of customers. So on the demand side, there's a range of options, which I think some people are talking about this today in terms of battery storage and load shifting. The two ones that I'll be talking about is dynamic access to network capacity. So this is a new type of arrangement where we're shifting from our traditional static access and assessment to network capacity, where we're basically publishing network capacity real time, and network tariffs that Jared mentioned, where we're trying to drive efficient use of the network to increase network utilization. The figure on the right-hand side just presents one of the examples of peak shaving. So you could achieve this through, say, a battery storage unit. And this is just showing where for instance, we can charge during minimum network demand and discharge during peak network demand. And this basically allows for tightening of the voltage envelope if it was a voltage constraint, for instance, within the network. So just talking to an example and the dynamic connection arrangement that the Future Networks team is currently working on. This figure presents a low duration curve, and this is for an example industrial facility on our network, industrial feeder. Oh, sorry, I've got stuff popping up here. And a low duration curve, as I mentioned before, was basically, if you look at 365 days in the year and you sort that demand from largest to smallest, it helps us assess the utilization of that asset. So this is a total feeder. And as we can see here, for the majority of the year, the network's sitting below that peak demand. So if we had a mechanism, a way of signaling this spare capacity real time in the network, we can connect and guide flexible loads to use that spare capacity, which that's the whole motivation behind shifting from a static connection to a dynamic connection. So effectively signaling real-time capacity in the network real time. And this things to etes units, as I mentioned in the last presentation. Linked to this, we're also looking at tariff innovation. So as I mentioned, about 1/3 of our network in the middle of the day is operating at reverse power flows or zero carbon, driven by the uptake of renewables. So on a dynamic basis, so combining that dynamic operating envelope with what we call a sun soaker period, so where the local use of the network, we've got solar PV locally. If we can soak that up with local load, we're only using the local network. So we can charge on that local use of the network rather than, say, HV and sub-transmission and end transmission. So this tariff structure, as it stands today, is what we've proposed. It's not yet approved by the regulator, but we're trying to introduce a much lower cost period, and this typically aligns with lower wholesale pricing as well, which we're looking at trialling this type of tariff with a couple of large industrial customers across our network with etes units. So I'll just talk about an example of alternatives to building the network. So this is where we're looking at an industrial facility that has dual fuel. So their boiler is not end of life. So a facility, for instance, has an LPG boiler, and we're running analysis on connecting an etes unit directly exposed to the wholesale market. So just explaining this concept back to that low duration curve. So typically for only about 3% time duration in the year, so say 10 days in the year, if you accumulate that time, the network is under stress. So during that time period, we're looking at the economics in terms of running that LPG boiler. And then during lower demand times on a dynamic basis, as I mentioned before, we would be signaling real time, the spare capacity in the network. You could look at basically a blend arrangement to meet your on-site daily heat needs, or where there's significant spare dynamic capacity in the network, run purely on electricity. And I should mention this presents the 100% time duration in the year, where, and say for instance, an etes unit has the advantage of storing energy, so you can tap into that super cheap, low carbon energy during the middle of the day. So you don't actually need 100% access to the network. So you can sing in tune to, say, this lower end period where demand is low, and that's what we're exploring as part of this trial. So an example here, for instance, this presents the top 10 days in the year for this industrial feeder. So on those 10 days, you'd typically run the LPG boiler or a blend of LPG boiler and the etes unit. And this presents the wholesale costing. So it's a mixture of the dynamic operating envelope and also the pricing at a wholesale level where it's cheaper than gas to charge your your etes unit. So onto resources. We've got some publicly available capacity maps to guide you in terms of what spare capacity there is in the network. So currently publish that with indicative spare capacity at the distribution sub-level. And we are also working on high voltage capacity maps as well. So basically feeder level type modeling to provide indicative spare capacity. We've also got network asset maps. So there's a link there as well, publicly available, which shows indicators of our feeders and our zone substations. And I should also mention around connection information as well. So if you are thinking about connecting to the network and you want to know what spare capacity is available, the current arrangement in New South Wales is you engage what's called an accredited service provider, and then they contact us in terms of through the connection inquiry process to extract information, and then they go off and do the designs, and they also construct if you then decide to connect to the network. And just recapping our electrification program. So as I mentioned before, we're supporting customers on a least cost path to decarbonise, and linked into this, we're supporting a number of feasibility studies to unpack barriers with representative customers per sector, to work with industry on solutions to try and accelerate decarbonisation. And we're also trialling emerging electrification technology. So for instance, etes type units with innovative connection standards and tariffs. So that's about it, but happy to answer any questions or shoot me an email or call me after the webinar. Thank you, Jared.
Ian, thank you so much. That is a fabulous comprehensive program that Essential's working on. Well done. Really, really going to help enable electrification. And I did love that slide 9, I think it was, showing the hybrid, how a hybrid solution could work with working with gas on those peak times and a little bit of gas and electricity combination, but 85% of the time the network's there for your electrical capacity. So yeah, really, thank you so much. Well presented. If there's some questions for Ian, throw them in the Q&A and he'll be able to grab those as we move on to our next speaker. So we'll keep it moving and hopefully we'll read them out at the end. Let's keep moving now, and we're going to James Diliberto from AZZO. James is an electrical engineer. His second webinar with us after last year taking us through harmonics and power quality and what have you. We thought it'd be great to get James back because he really understands the idea of metering and monitoring and controls and how that can improve your electrical utilization. James, we've got those slides up. Over to you. Take us through it. Oh, just on mute there, buddy.
Perfect. All right, that's good. I'm glad I'm not talking to myself. Not that I don't ever sometimes do that. That's okay. I guess we all do a little bit of that. So thanking you for inviting me to speak again. Also, want to special thanks everybody who is in the attendee list that we know. Some of you are absolutely experts in this field, so we won't be telling you anything that you don't know probably today, but we definitely look forward to your engagement and any insights you want to add in the Q&A, and also the very many of you who are on the list that I don't know. So quick agenda, what I want to do, this is going to be a lot more about storytelling. Well, there are plenty of graphs and concepts, but be mostly about storytelling, a little bit about background and my personal experience with this. Sharing what we do, our mission and purpose in order to create the outcomes that we've just been referring to, a couple of key principles, some case studies, and then some take-homes to remember. So background for me, whilst I do run AZZO as a business, I am a chief geek. I love this stuff. I'm principal engineer and couldn't be more excited to be sharing hopefully what are technical things in a simple to understand way, I hope. Now, a little bit more about me. I live in AusNet. I live in a little private road called Cypress Place, and I don't always have wine with my neighbors out by our switchboard, but I have been more recently because there have been some builds happening on our little private road. And as those builds have begun, we've realized that we don't have enough of everything. Not only do we not have enough space, but we also don't have enough capacity for some of the things that these new builds are trying to achieve. So I have had to watch Downer out there at the transformer on the pole, trying to figure out and pull their hair out a little bit, trying to figure out how they can get some more capacity into our street in order to provide some things, not only for electrification, EV chargers, but also with an aging population in our street. Some of these people need elevators, and some of which require 3-phase. And unfortunately, if you have a 63 amp service and your elevator requires 70 amps, you're in trouble. So unfortunately for many people on our street, they're finding with electrification, adding EVs, electrifying their homes, or maybe even adding an elevator, they just don't have enough juice. And whilst we get these sometimes on our computer, that's nowhere near as problematic as it happening on the place of your residence. So what I've done at my house with my electrification is I've actually gone through and went, okay, well, can we solve this with other means? And so my electrification journey for electric vehicle charging and electrifying my house was a technology integration. I've got battery storage, solar, EV charging, all working together in a bit of a closed system. And that means I don't need as much power from the street as I would otherwise have needed. I generate it, store it, and dispatch it as I need it required locally. And that, as far as what we do as a business, that we kind of find ourselves in the place where if we can solve this problem through technology integration, through good system integration, modern energy IoT, and some sets of services to go around that, maybe we can solve this also for C&I and utility customers. And of course, that's what we do. Now, as far as our mission, I truly believe that integrated technology is how we're going to enable these energy transformation initiatives. It requires a lot of dynamic skills. To solve this, we need energy management, electrical engineering, power automation, and digital systems all working together. So as far as what we do every day, what I do for work is not too different from what I experience and need at my house, and what the market and what the rest of the country is needing. So it's just a little bit of further need. So start HUEP, you get on this thing, I'm quoting something from the EEC. These are sister organizations, but I highly recommend that for the attendees, you go have a look at the Clean Energy, Clean Demand publication from 2023. I think it will help understand that it's not just about getting clean energy, but it's also about how the demand works. And I think that's just a good principle. So for our attendees, that's certainly a good read. A couple of really simple principles here. Fundamentally, first one is, remember, when we talk about some of these power quality concepts, what we're talking about here is kVARs, kVA, and kilowatts. The classic beer analogy, remember that when we talk about transformer capacity, we're talking about kVA demand, no matter how efficient and effective that power is. So we are talking about the best pour while retaining a little bit of kVARs. And when we're talking about energy and demand, when we're talking about demand, we're not talking about volume here, we're talking about rate. So to that end, just making sure that we understand, we are talking about right now avoiding the size of the engine required to go a certain speed, not necessarily distance traveled. So I hope that that just fundamentally makes sense for anyone who's watching this, looking for a metaphor analogy to compare. Now, I want to just talk for the rest of this session, give some examples about a couple principles. First of all, core principle, you can't control what you don't measure. If we want to have any chance of controlling these things or determining what to control and how to resize and how to even interface with essential energy, we need to do measurement. And fundamentally, a tech stack doesn't have to be ours, it's just an example. A tech stack, in order to do that, is essential. No, not there to essential energy, but it is essential to unlocking the energy ecosystem. So our philosophy is you need some things operating at high speed at the edge to manage these real-time demand requirements, but also to, as was mentioned in the previous presentation, to be able to forecast and anticipate what those things are. We want to use modern software, not just ours, there's plenty of other examples out there, to be able to look at the forecast, look at the pricing, connect with other stakeholders to be able to manage the demand at the edge. So you need a tech stack in order to do this. Anyone trying to do this manually, running around with castle keys and breaker switches, it's just not going to work. And thankfully, we don't have to do that in 2025. Technology solves this. So let me give you a couple of quick examples. One, these are all redacted, but they are real examples that are under our management today. First, a shopping center. They were being faced with a large transformer upgrade to put in a new wing of this shopping center. Well, instead, they put a large amount of car park solar and then implemented a demand management system, taking advantage of the building envelope and making sure that the loading and unloading of the chiller management system on site was done in such a way that it could avoid avoid having to upgrade the transformer for those rare times, as the previous presenter showed on the duration curve, that you don't actually need that much capacity. If we could manage it in a shorter, faster amount of time, we can. And that's a great example. So maybe you or your customer is a shopping center. Great example to avoid a large transformer upgrade. Another example, big meat abattoir, constantly adding capacity, wanting to transform, wanting to decarbonize, just didn't have a big enough transformer. So why not install a large amount of solar behind the meter? But because of the variability of load and the forecastability of the solar, needing something to manage that, insert a battery. So for example, on this curve here, you can see a forecast of 1.5 megawatts, but if that jumps up to 2.2 megawatts, what are you going to do instead? Well, you can't rely on your solar, because the solar at this exact time dipped, a small cloud came over on that day, and that is exactly where the battery kicked in. So that little blip there on the duration curve that would be right up towards the front on the left side was able to deliver that extra capacity that otherwise would have been required to come from a larger transformer. Great example. Another example, food manufacturing. This is where the introduction of energy efficiency opportunities like variable speed drives to manage starters, well, that actually created some challenges with harmonics, which could then be addressed by active harmonic filters. And the bottom line is, the actual amount of challenges that were coming from their own transformers manifesting in voltage sag events was mitigated significantly by, again, installing technology. I'm going to quickly go through this next one. This is an example where we have large-scale chargers. So this is fast chargers in a small location with a small connection. So rather than paying $500,000 to install a larger transformer, why not install some PV, some battery storage, and have that all controlled in such a way that prioritizes the load control and then takes all the secondary benefits like spot market participation, frequency ancillary services, while it's not doing that primary job. But the speed to get those chargers in and to use them was extensive. Also, just another example of that, whilst the battery is not being used for that, it can also be used for things like arbitrage and other things while it's not being used for peak management. And then, of course, actually controlling those chargers, all of those things working together avoided the transformer upgrade. And then the last example, large bus depot in the United States. The government is committed to decarbonizing, transforming all of these buses to electric, and there was just no world in which that was going to be possible without putting some monitoring and real-time controls in. So this is a great example of a limited feeder from the utility there in Washington, D.C., integrating it into a full microgrid with lots of kinds of generation, as was said earlier, hybrid generation. So this has some gas peakers, some solar, some batteries, and some load management of the EV chargers all happening at the same time. Now, that's a lot of EV chargers to control, but again, with technology, that can all be sorted out. So let's take it home. Some nuggets of some things that I hope you learned. First of all, you pay for not only how far you go, the cumulative distance that you've gone with kilowatt hours and energy, but also how fast you go, kilowatts to get there, or kVA in a transformer capacity. Power factor directly impacts transformer sizing. That can be addressed. More power quality themes, harmonics, and unbalance can also stress those transformers' capacity and their lifespan. The transformer size at the point of connection is not the only lever for load needs. DERs, as is going to be mentioned by Stace very shortly, can obviously help. We got some examples of that before. Stace is going to talk to us more about that. You can solve most issues with integrated technology. And lastly, solutions.azzo.com maybe is your Obi-Wan Kenobi. So if sometimes to avoid a transformer upgrade, you just need integrated technology. So start it with measurement, find out what's going on, get some good data, and then do measurement today, do controls tomorrow, and then you'll get a win for the planet and a win for your pocket. Thank you.
James, awesome. Nailed it. The coffee paid off. Thank you so much. And Really glad you brought EVs into this as well. We're often thinking about renewable heating and electrification of heating, but EVs is going to come up and this is going to be a major thing. Could you give us, putting you on the spot here a little bit, could you give us a quantum of investment here to look at the control? I mean, if you're looking at that extra 1 MVA of transformer, it's probably going to be about $1 million. What could we do with controls and data instead?
Yeah, well, the first thing before you go out and start buying a battery, it's if that's the only thing the battery is doing, it's not a good use of that. So you first start off with measurement, then see what kind of load flexibility you have, see what kind of staggering can be done. I mean, the project for the shopping center was about a $150,000 project that avoided a $1 million transformer upgrade.
There it is.
Then they added solar on top as just a way to mitigate having to flex as much as you would have had to otherwise. That's a great example. The EV charging project was about a $60,000 investment,
Okay.
and then obviously the battery on top of that. But the controls and monitoring for this stuff is not hard, and that should be your first point of call. And then you have the right amount of data to size the stuff that Stace is inevitably going to talk about. So be data driven. Don't just hop at the next thing. Measure, determine what's required. And all of the technology exists to manage these things. You're going to ask for a transformer upgrade should be the last thing you do, seeing as the tech is already there to support it.
That's it.
Thanks, Jim.
Perfect. Thanks for those examples. Really good. Okay, so James has taken us through the monitoring controls and how to implement the BESS and what have you. But let's now turn to overall lowering that energy, that electricity demand. And for that, we're bringing in Craig Morgan. Craig, with 30 years experience in this field and done more energy audits than I've had hot dinners, how could this be the first time we've got you on a webinar? I don't know, but great to have
I know
Northmore
either.
board in here, premier organisation for energy consulting in Australia. But great to have you here, Craig.
Well, thank you. And I do feel a little bit like I'm talking about some of the first principles that I learned when I was first doing energy audits in the 90s. So for some of you out there, it may well be that, this is well known, but it's worth reiterating. And just the same as James was talking about, there's many things you can go to before you need to step to the transformer upgrade. And these benefits are really stacking. So measure and monitor, you'll see that a bit today in my presentation. Having flexibility to use lower network tariffs. I'm glad the networks are really stepping forward with that opportunity, and controls and data is always going to help. So how can we avoid grid upgrades through energy efficiency? A little bit about us. Our purpose is really to help large energy users have a positive impact, not just minimize negative impacts, but have a positive impact on the environment. And we combine the value of environmental certificates with expertise in large energy using companies. I don't talk a lot about certificates today, but by going deep in energy efficiency, not only do you avoid the transformer upgrade, you can also, put yourself in a position to unlock funding from environmental certificates. So in our studies of electrification and energy audits that we do find electricity on site is almost always constrained one way or another. It's either limited by the site, by the grid supplying the site, or it's not evenly distributed around the site, the capacity that is in switchboards. It's switchboard location and capacity is often driven by expansions to production, where they need it at the time, minimizing capex. They just steal power from other switchboards. There's all sorts of things go on site. Individual switchboards have cyclical peaks, whether that's weather-driven, affecting chiller systems, or product lines, or seasonal demand for, say, food and beverage, for example, might drive seasonal peaks on switchboards. So what to do if, for example, electrification exercise, or in this case, a heat pump, overshoots the available electrical capacity, the size of the required heat pump? So, well, I guess you could size the heat pump to do the job and just pay for the electrical upgrade. You can size it to the available electrical capacity, and that's certainly something we're recommending for some customers, is that partial electrification is a pathway. Or you can use some of that avoided money you might have had to pay for electrical system upgrades to go a lot deeper on energy efficiency. And that way it means you can potentially size the heat pump or the electrification project as large as possible. And because you're going to get energy savings as well, it's probably the highest NPV option. And today, as I said, we're kind of going back old school here, focusing on air compressors, refrigeration and chilled water, and pumps and fans. Air compressors, for those of you who haven't been around air compressors a lot, you're probably not surprised, but I guess to point out that the total cost of ownership in air compressors is 80% dominated by their energy use. And so they can be a big consumer on sites. 3 to 7% might be, say, a typical manufacturing site, food and bev, for example. It can be a lot higher on smaller sites. And the largest I've seen was a 15 megawatt compressed air system in a shipyard, and it was 40% of site use. They're quite exceptional, not typical, I would say. So what do we do with air compressors? Well, I'd have to say, jumping forward to my final point there, I can envisage today when plants are going to be built with no compressed air at all. I think that's actually something that is coming. So in terms of electrification, get rid of compressed air and you'll reduce demand and as well. But opportunities do abound, and we generally split those into supply side and demand side. And as I take you through this, you'll see that 50% savings is not extreme, it's entirely possible. Air compressors are easy to buy, easy to install, and if you include the dryers as well, easy to run inefficiently. So we have done a lot of measurement of compressed air systems. So we're just talking about the supply side here. We're talking about going back to this adage of you can't manage what you don't measure. The specific energy consumption of compressed air can be measured in a number of ways, but put it simply, energy in, air out. And what we found in measuring over 30 systems is that over half are twice the sort of ideal or best practice specific energy consumption. So that's from real data, average industry, 30 sample points across a range of pressures. You do tend to find the bigger sites are around the lower SEC, so closer to ideal performance. But overall, it's pretty hard to walk out of a site and not have some good opportunities for compressed air. So this information can be found in this diagram here, can be found in the New South Wales government publication, I Am Your Compressed Air Guide. Full disclosure, we did help contribute substantially to this one, so I like it. But it is actually, the government themselves did this drawing, and I think it's a really good way in one page to capture the opportunities in optimizing compressed air. And one of the biggest opportunities on the supply side is really just getting your sizing and your sequencing right for your compressors. So sometimes that does mean a new compressor, other times it just means controlling the ones you've got better. And there are many options to do that. On the demand side, only one of these 15 actions is about leak management. It's a big one, but it is only one. There are many other things you can do to reduce demand. There's two examples I'll just give from recent observations in humid environments where dehumidifications of compressed air is really important. We had a site that was losing 20% of the total air they generated through the desiccant dryers because it was just on a timer-based control. Equally, they had some wastewater pumping applications, and they're using compressed air vacuum pumps and compressed air diaphragm pumps, and they are just absolute beasts for sucking up compressed air. And there are alternatives. There are electric-driven diaphragm pumps. You don't need to throw away the diaphragm pump. You just need to electrify. So there are many, many options, everything from system design to maintenance to avoiding the use of compressed air completely. Oops, wrong way. Oops, what am I doing here? All right. Okay, so jumping over to refrigeration. Now, refrigeration has a lot of similar opportunities because you have several compressors in a system and you're looking to optimize overall system efficiency. Up to 40% demand savings are totally possible, and we've seen it. I saw it 20 years ago. There was one of the first really big VSDs went in on a brewery site to control the refrigeration compressor. They put floating head pressure control, 30% measured and verified reductions out of that system happened once the project was done. And that's 20 years ago. And there's still many, many systems around that don't have that capability. And also things change as well, right? So we know that production on a lot of sites changes. And so what that means is low-hanging fruit does regrow. You would have heard that saying before, because the load profile of things change, which means that the system you have may not be as adaptable or as efficient in delivering that particular load. Another good example, I haven't got a chart here, but we measured a bunch of chill water systems and water-cooled chill water systems. Singapore love a good standard. They have set a standard, and they've set a standard for how you measure these things. And for large systems over about megawatt refrigeration, the target delivered through existing technology, known technology, and good control and management and good system design, not any more expensive than a badly designed system if you were putting it in new. The target is around 0.64 kilowatts per RT for a system delivering, say, 6 degree, 7 degree chill water. Most of the systems we measured delivering that temperature were at 0.8 to 1.2 actually. So we know when you put measurement on these things, they are not operating as efficiently and as they could be. And the big question at the very start of, if you look at just compressed air and refrigeration utilities delivering to a plant, do you know your system efficiency? Once you do know your system efficiency, that's just delivering the utility efficiently, then you can go through all these opportunities to reduce consumption. And it reduces not only consumption, but also the total kilowatt demand. So what that does is frees up headroom in your switchboard that allows you to electrify further in areas of your plant. So in sizing though, or working out, particularly in a refrigeration system, how much peak demand you're going to reduce, there are some important things to consider. It is different than compressed air because maximum demand can occur on that refrigeration system at peak times, on the hottest day with the largest refrigeration load at times of highest production. So then you can go beyond that and say, well, what coincident loads are happening at that time? Can we manage them? Can we look at thermal energy storage? And in this case, I'm not talking about hot energy storage, I'm talking about cold energy storage. Ice systems have been in place in the industry for a very long time. In fact, they went out of favor. Everyone was ripping them out. Now, I would suggest put them back in. They're not new. They've been around for years and years and years. And just make ice during those times that Ian's going to give you a great network tariff and the wholesale price is down, and just run chill water through that. And they can be hours of storage. And it's a battery, it's just a thermal battery. So I'm sure that James could manage that as much as an electric battery could manage a thermal battery or a cold battery. There are other ways to avoid peak loads by floating process temperatures, cool store temperatures, either down or up. So pre-cool if you know you've got a peak coming up. Managing variable loads, and I've already talked about sort of cold storage. This is just another set of data that reinforces how efficiency in systems varies substantially. You can see the source there, you'll get the slides. I'd recommend you go and have a look at that. There's a lot of work being done on mapping the efficiency of systems. And finally, I feel like pumps and fans have been forgotten. They're up to 40% of some industrial sites. High system efficiency is the goal. So efficient motors running in their optimum load point. Efficient pumps, good impellers, well designed. Efficient fans, big fat pipes, as slow flow as possible because of the increasing energy consumption exponentially with increasing speed through ducts and pipes. Good controls. VSDs are really common these days, I'm sure, but there's still lots of systems where there's high volumes of recirculating flow, and we know that you can replace fans with, in particular, fans with EC fans, cooling tower applications, air-cooled systems, fan-cooled units, AHUs, etc. So all of those things help reduce a base load and creates electrical headroom for you to do those other electrification things before you go and buy that transformer. In addition, you get savings. So energy efficiency is that great decarbonisation tool, create a electrical headroom whilst getting you savings at the same time. That's it. Thank you.
Craig, brilliant. Thank you so much. So we often say if you can't find 20% energy efficiency savings, look harder, or maybe you don't have the data. So I think that's reinforcing there. If you look at those three options, surely there's going to be those the savings available. And once again, we hear controls, controls, controls. In terms of payback, I don't think you can beat controls. So Craig, awesome data and presentation. Thank you so much. We've got a few questions coming through there, and they look like great discussion points. We'll try and get to them, but Ian might like to answer a few in the Q&A there already, and we'll read them out at the end here. But we're going to kick it home now with Stace Tzamtzidis from GridBeyond. Stace has been working in the distributed energy resources industry for many, many years with batteries and solar and PV. And so comes to us with a wealth of experience and no doubt plenty of good war stories and recommendations of how to do this properly. Stace, you've probably seen a fair bit of change in your time, been around in this industry for so long, and still plenty coming. But over to you, Stace, to take us through some recommendations on how we can utilise these resources to avoid that electrical upgrade cost.
Thank you, Jared, and thanks to other speakers. A lot of the issues, a lot of the topics have been touched on, so some of my earlier slides I'll run through, but my name is Stace Tzamtzidis. I'm the Regional Director at GridBeyond, and I'll be building on the comments of the previous speakers and taking a deeper dive really around what value behind the meter batteries can bring. First, a little bit about GridBeyond, because we're a relatively new company in Australia, but we've been operating in the UK since 2010. We operate in Ireland, UK, Australia, Japan, and the United States. We just closed off our first 200 megawatt project where we're providing optimization services in the Texas market. But we're essentially a software company. We're AI-driven software for demand response, behind the meter and front of meter battery energy storage. We operate industrial loads, EV chargers, etc. Our platforms enable asset owners to optimize revenue by participating in the energy markets, including FCAS, wholesale trading, and grid balancing services. And our software solutions, we break up to three broad categories. One is intelligent forecasting, optimization of bids, and then automated trading and settlement. A lot of this has been copied already, but the blockers to electrification of the grid, which is really the basis of this webinar, is the electricity grid is evolving from a centralized distributed grid. It's something that the grid was never designed to do. And also we've got capacity at each individual connection point, your factory, etc., or an industrial complex. So you've got various options. You can invest in grid upgrades, or you could invest in upgrades, or you can invest in other technologies such as energy efficiency or batteries. With congestion comes a number of problems, not only including the inability to connect, but you also introduce voltage and frequency stability issues through renewables, introducing harmonics and voltage sags through intermittent supply. You've also got connection delays in the cost, and also the infrastructure is aging, and that's also posing problems. So here's a map, and I think this was touched on by Essential, showing a screenshot of South Australia from the DAPA website. This is all readily available. The options that industrial customers who want to increase their electricity consumption at site, they've got various options. We've talked about it. You can do an upgrade to transformer, substation, or transmission line. It will take some time. You can do load management, demand response. That gets you part of the way there, and that's probably a good starting point. You can install on-site renewable energy such as solar and wind. That will reduce your energy costs, but the intermittent nature and insufficient capacity may not coincide during peak periods. On-site battery storage is the area that I'll be sort of honing in on. Install a battery in lieu of a transformer or upgrades to the switchboards or the lines. So let's look at online battery storage. You've made the decision to install a battery after you've done the PQ measurements, you've done your energy efficiency, you've fixed up all your air, etc., etc. So how big is the battery? What sort of battery do you need? And I think James touched on it with his Lamborghini Camry analogy. There's two parameters you look at, is the megawatts or kilowatts, or the megawatt hours or the kilowatt hours. So in this example, we've got an industrial customer with a 2 meg connection. His peak is 1.5, so everything's operating. There's no need to install a battery or do a network upgrade, but he puts in a new production line and his average load increases to 1.3, which isn't the problem, but his peak load is the problem, increasing at 2.5. So one option is to introduce a new transformer. That may or may not be possible depending on where on the grid he's connected. He may not even get a connection approval to go to 3 meg or 4 meg. So if we had a peak of 2.5, the battery will be determined by how long do you need that, how long does the battery need to operate. In the example that James offered, he had a small spike, which meant not much energy, which meant not many megawatt hours. But if you've got a 1 hour duration spike, you'll need to match it, which is a 500 kilowatt in this instance, 2 hours. So it's proportional to how long that spike is there. The 500 kilowatts is the amount of energy or power above the connection limit. In this case, it's 500 kilowatts. And then I've matched it up with solar PV. The solar PV is the calculation I used was 1 kilowatt of solar produces 4 kilowatt hours on average. And that's enough to charge the battery. Now, these are the minimum numbers that you need, and this is only for ideation. These are not detailed calculation, but it gives you an idea of how big that battery is required and how big the solar is to overcome the problem. So you've installed a battery, you've installed solar, and the whole idea behind it was, I want to avoid CapEx. But then you've got an asset that's sitting there, probably working a few times a year. What else can you get out of the battery? And this is where GridBeyond can add additional value. So when you look at the battery value stack, there's 3 areas that we break it down to. Grid services. This is the battery participating in arbitrage or energy, FCAS. Capacity market, which is future, and grid forming and system strength services emerging. These can all be monetized. They've all got value. And the software that you use can unlock that value. So I'll park that for a minute. Utility services, this is really helping out the network operators at the transmission and distribution level. The question there is, are they prepared to pay for it? And if they are prepared to pay for it, what are they offsetting? So in a lot of cases, if they don't need to update a transformer, they have a 50-year life on that transformer, they might say it's worth 1/50th the value of the transformer. That's what it's worth to us. Whether it's worth anything to you as a battery operator is a decision that you need to make. Then you've got customer services. Because these batteries sit behind the meter, you can participate in grid services, but at the same time, you can reduce the energy bill of the consumer or the operator of that site. You can do it through peak demand reduction, load shifting, solar maximization. No longer exporting solar, you can store it and use it later. These will all translate to energy savings on the customer's bills. We've also can introduce things like voltage support for sags and swirls and backup power. Now, the value of those won't be translated on the energy bill every month, but where they are translated is the loss of production time. So if you've got a voltage sag and it turns off your premises, and then you have to restart your machines, and that's cost you $20,000 worth of lost revenue, that's the value that a battery may bring. So if you've got a problematic site where there's voltage sag, swirls, harmonics, after you've gone to James and he's fixed all his problems with harmonic filters and power factor correction, and that problem persists because it's coming from the network, then a battery may be the option. So this is an example of a battery, and I picked the Torrens Island BESS, and this is at an industrial scale, but I'm getting the same point across. And because I'm based in South Australia, that's why I'm using this battery. You see there's 3 major revenue streams that are reported. There is additional retail hedging that the battery operator does where we don't see, but we know it's all the capacity market, which we don't see. The top represents energy. So you're buying energy low and selling energy high. The second one represents regulation, FCAS, and the third one represents regulation. Sorry, the second one is contingency, and then regulation. Pay particular attention to the scale on the left-hand side, which is the dollars. So you see the energy, the slide is up to 3 million. The second is up to 2 million, and the third one is up to $20,000. So you'll notice that the events are random or appear to be random. They do coincide with things that are happening on the network. And the battery will trade into this, the battery will trade into the market with a profile similar to this. So when you build a battery and you want to extract additional value, is what is that value? So if you came to us and said, what is the value I'm going to extract from my 1 megawatt or 5 megawatt battery I'm putting behind the meter, we will provide a forecast. And our forecasting algorithms go out to multiple years, and we can do short-term forecasts, long-term forecasts. But to mitigate risk, developers rely on companies such as GridBeyond to provide that market forecasting, and then the trading optimization, and then the automatic settlement of services. So what does the forecast look like? And this is an example of an energy forecast in South Australia. And you'll see there's two graphs there. One is the forecast energy, and one is the actual result. And you'll see on the right-hand side of the graph, there's no actual, because what we're showing there is the next 4 hours. And this is all programmable, is the next 4 hours and the next 24 hours. So what we're saying to the market at this snapshot in time is, for the next 4 hours, there's going to be negative wholesale prices in the market. And this is an opportunity for you to charge the battery if you've got a battery at low cost. This is an opportunity if your industrial building is on spot markets to run your machines. Because some industrial sites will run their machines during low prices, and when the price hits a certain threshold, they'll turn everything off. And there's one customer that we're working with that does this. So just the forecast itself, if you've got an industrial complex on spot pricing, will help you decide when to operate your machines, or in the case of a battery, when to charge that battery. This is an example of regulation FCAS. And again, we're showing the raise and lower. We're tracking the actual to the forecast. And in this instance, we update our bids every 5 minutes, sorry. So we're showing 5 minutes in advance. Once we're locked into a bid, we're in the market, and then we're reforecasting for the next period. So with regulation, we're really looking at what I call a steady state frequency event. It's like driving a car down the road. Regulation, FCAS for me, is you're just driving straight and making minor adjustments to the steering to keep you on the road. But with contingency, it's when the kangaroo jumps in front of the car, or when the frequency goes to more than 0.15 hertz. So contingency is ad hoc. It happens when there's a network disturbance, something disturbs the network, and you see it's not as steady state. And it happens when there's a network disturbance. And there's 8 markets to participate in: the 1 second market, where all the value is, right through to the 600-second market. So one of the services we offer for large industrial complexes of refrigeration or smelters or arc furnaces is that we can enroll those assets into the frequency market or FCAS services, where we can turn off a device for anywhere between a few seconds to a few minutes, and that could earn a lot of income for the operator. So we've got 11 data points. We've got 8 contingency FCAS points. We've got 2 regulations. We've got energy. So which market do we participate in? So what happens is we generate a forecaster. This is a heat map showing the probabilistic outcome versus price. The red represents high probability events, high value but less frequent. And the blue represents more frequent events, lower probability, but lower value. So the question is, where do you participate? And this is a 5-day cycle. So the sun comes up every day. So we see some sort of repeatability. Well, the answer is it's like playing snooker, and I'll use this analogy. You're not playing for this shot, you're playing for the next shot. So if you discharge your battery now at $40, there might be an event in a half hour's time that's worth $160, which our forecaster will identify. So you make a decision, or our optimizer makes a decision, don't discharge now, wait, and in 1 hour's time, there's more revenue to be made. Or when the prices are low, charge your battery. So how does that look like? It looks like this. The top represents the value stack of the services that happen in real time, or the potential trading. So it might be a mix of energy and FCAS. The bottom represents when we're charging and discharging the battery. So during period, the red on the bottom represents energy prices are low, so I'm charging my battery. The blue represents energy prices are high, so I'm discharging the battery. And the purple in the background represents the battery state of charge. I operate the battery inside the manufacturer's limitations, say between 3 and 95%, and I maintain it to 1 cycle a day. So I operate the battery based on what the batteries allows me to do to maximize the revenue. The bottom line is, it's a total solution. It's through measurement with AZZO, it's optimization of services, fixing the low-hanging fruit. And then if you do decide to put a battery in there, what additional value can you extract from the battery? A total solution provider should be able to give you a revenue forecast of what the battery should produce, what the cost savings would be to the retailer, and those two numbers, and plus the offset in capital from the transformer. And that's how you make a business decision. So thank you.
That's it, Stace. Well done. Thank you. And I mean, it's just such a different asset to putting in solar PV. Once you add those batteries in, it's a Swiss Army device these days. It can do so much. So exactly why you need help with controls and that. So very good. And now we can see how bringing in that battery is going to help not only help with avoiding the transmission upgrade or the transformer upgrade, but also with other revenue as well. Brilliant. Thank you so much. All right, let's see if we can kick it home real quick here. Ian, I see you've been answering a few questions there already. Thank you so much. And the one I was most interested in was the network companies. Are they all sort of discussing approaches with each other? And you've said, yes, they are. They're working with other network and government industry associations. But I've got to say, we still don't quite see them nowhere near as progressive as Essential Energy with what they're doing. I know that Ausgrid are trying some different pilots, Endeavour are thinking things, Sapin has a very much a residential focus. I think there's a lot of learnings that the networks can get from each other. So glad to hear you talking there. Not sure if there's anything further to add on that one though, Ian.
Yeah, exactly what you said. So we're working with other networks. We are finding other networks are probably more focused, as you said, on the residential side. So we're definitely talking to what we're learning through working with customers and industry associations around industrial decarbonisation, as well as government. That's a key piece. So we need to be working collaboratively across industry. We can't be developing these solutions in silos. We need to be working with everyone to unpack barriers and develop solutions. The only way we can do it.
Got that right. Question here from Chris about DQ using time of use emission factors. I'm aware of studies done with Race for 2030 on this true net zero. Craig, are you up to date with what they're thinking of time of use emission factors? Anything there that you're aware of?
We did get asked by someone to look at time of use emission factors because they were operating a battery as well, right? So they're looking at taking it from the grid at times of excess solar, so the dynamic emission factor is quite low, discharging at times of higher emission factor, and then really just wondering how do they report all of that in their ENGA reports. So the context that we were looking at it was really in that context of can I report a battery as being a lower emission output than the grid at the time, and there was a liability for LGCs and use and losses in the system. So that was the context. So apart from that, I haven't had much to do with dynamic emission factors.
We'll have to look into to see what that's progressing. We haven't done a lot in this sort of policy space as A2EP, but if you look at OpenEM, it's already there with the the data's there on grid emission factors. Sorry, Ian?
Yeah, I was just going to say exactly what you just said. In the previous webinar we did about a month ago, that's what I talked to New South Wales perspective. I think it's better in other states, is in the middle of the day during peak solar PV production times, we're pretty much on par now in terms of grid carbon intensity with natural gas and LPG, and that will continue to decline year on year. So definitely our advice to government, and we're working with government, is that the various schemes that are used to calculate ESCs and carbon reductions, 100%, we need to be going to time of use carbon intensity calculations. And not only does that identify to say, you know, you're investing in a 30 to 40 year asset, noting that grid's effectively zero carbon by 2030. And as I said, about a third of our network today is zero carbon during peak solar PV production times. Having those calculation methods and aligning load to those times will also support the connection of additional renewables. So we can actually bring the curve forward and even, you know, it'll be earlier than 2030 in terms of getting to zero carbon grid energy.
Absolutely. We might look to, we had one suggestion earlier in the webinar about looking at a low temperature etes. We might have to take a look at this emission factors, time of use, and get an update from the clean energy regulator there. There's a lot going on there. There's a couple of questions that have come through, like on EV chargers. And James, I might connect you directly with Vincent, who's got that question on the EV chargers, having problems there with the local council and problems. James, should we just take that one direct?
Yeah, more just to say that that data early to know how stable are things in the grid before you start introducing big variables like higher powered EV chargers, just to know the state of play first before you do anything. Again, measure before you control. So that's for everybody, but in that particular case, we've faced that in a number of places where the grid was already constrained in that area. There was already neighbors that were experiencing problems, and just to get a stethoscope first before you start diagnosing cures.
Get the data. That's the one. Thanks, James. And the question there on the refrigeration efficiency data from Peter. I'll email that one to you directly, and we'll try and get that emailed out to everybody with the slides. That excellent publication as well. So I think we've covered off most. If there's a few questions left, we'll try and get those covered, and we'll put them in the slide deck when we put those out. So I'd just like to say thank you very much to our panel today. That was a great round of presentations. So many thanks to Ian, James, Craig, and Stace. To wrap up now, just let you know what A2EP has going on. Hopefully we'll go to the next slide. Yes, computer is not happy. But coming up, we've got a few more events over the next month, of course. Looking at a site tour next week down in Melbourne, going to a winery with some heat pumps there, and checking out a brewery that's doing a lot with energy efficiency and getting ready for heat pumps. That one closes, I think, tomorrow for registrations there, so get in for that. We also have a member mixer coming up in the middle of April, and a few new workshops that we're doing, lowering the heating hot water temperature in commercial buildings, the absolute crucial step if you want to degasify and get into heat pumps for a commercial building. One of the most important steps that's being overlooked right now. Also to remind you all, we do have our renewable heat conferences back in August this year. Most of the sponsorships are sort of closing out, so if you want to get in there, you have to get in there quick, and we've got a stellar lineup coming with international guests and what have you, so looking forward to that one already. And if you want more from A2EP, as always, follow us on LinkedIn. You'll get plenty of news coming through there. So all that's left to say is thank you very much for joining us today. Hope the new time worked for a lot of you. Sorry we went over a little bit over time, but I think there was some great discussions we couldn't cut off there today. So thank you all for joining, and look forward to seeing you at our next webinar. Have a good day.